Okay, in this video we're going to do a little bit more of a review for exam 2, and this is going to be based more on questions that you've submitted to me. So one of the questions I've heard from several of you is what do we need to know from section 6.8, the section on the hyperbolic functions. So we only had about 30 minutes of class or so before the break where we touched on this, and so let me just give kind of a brief overview. So we have a couple hyperbolic functions here. They're called hyperbolic sine, it's also called sinh, and hyperbolic cosine, it's also called cosh. And so let's look at cosh first. So cosh of x is defined to be e to the x plus e to the negative x over 2. Now notice if x is a big positive number, so like say x is 100 or a million, e to the negative 100 or e to the negative million is going to be really tiny. It's going to be close to 0. So if x is big, cosh of x looks like e to the x over 2, because this part would be 0, the e to the negative x. Now, if x is a big negative number, e to the x will be tiny, right? So if x is like negative 100 or negative a million, this will be tiny. So the graph will start looking like e to the negative x over 2. So if we look at Desmos, the graph of cosh of x is right here. Notice it almost looks like a parabola. It's actually not a parabola. But if we graph 1/2 e to the x, that's in blue here. Notice the further we go to the right, the more this cosh of x starts looking like this 1/2 e to the x. And if we graph 1/2 e to the negative x and we go further to the left, the graph looks more and more like that. Okay, and by the way, cosh is very useful in different engineering applications. For example, if you hang a chain or a rope between 2 points, it's going to be part of a hyperbolic cosine curve. It's actually not a parabola. Okay, if you hang a rope, or say like a telephone line hanging between telephone poles, right? It makes a part of a hyperbolic cosine curve. It's not actually a parabola. Okay, then hyperbolic sine is similar, but it's e to the x minus e to the negative x over 2. So this one, if x is big, still looks like e to the x over 2. But if x is a big negative number, it will look like negative e to the negative x over 2. So if we go back to Desmos, let's get rid of these. If we graph sinh, okay, hyperbolic sine or sinh, it looks like this. It almost looks like kind of like an x cubed. It's not like x cubed, but notice as we go further to the right, again, it starts looking like 1/2 e to the x. But as we go further to the left, it actually looks like negative 1/2 e to the negative x. Okay, so that's what the graphs of hyperbolic cosine and sine look like. Now, one of the key things is that the derivative of sinh is cosh, and the derivative of cosh is sinh. Now, notice that's very similar to sine and cosine. The only difference is the derivative of cosine is negative sine, whereas the derivative of cosh is sinh. So it's actually easier with these hyperbolic ones because you don't have to keep track of the negatives if you do integrals or derivatives. Okay, so now why is the derivative of sinh cosh? Well, let's remember what sinh is. Sinh is really 1/2 e to the x minus 1/2 e to the negative x, right? So we can do this over 2 minus this over 2. So if we want to take the derivative of sinh, we can take the derivative of this. The derivative of 1/2 e to the x is just 1/2 e to the x. The derivative of minus 1/2 e to the negative x is going to be minus 1/2 times, well, the derivative of e to the negative x is e to the negative x times negative 1, right, by the chain rule. But then notice this negative and this negative can combine to become a positive. Okay, and so what we have is 1/2 e to the x plus 1/2 e to the negative x, which is 1/2 times e to the negative x plus, or e to the x plus e to the negative x, which is really just cosh. Okay, the definition of cosh. Okay, so the derivative of sinh is cosh, and you can do it the other way and show that the derivative of cosh is sinh. In fact, we have several other definitions. We define tanh of x, or hyperbolic tangent, to be sinh over cosh. Okay, just kind of like tangent is sine over cosine. Tanh, hyperbolic tangent, is sinh over cosh. And if you work out what sinh over cosh is, right, if you were to do this divided by this, well, it'd be like doing this times the reciprocal of this, and those 2's would divide out or cancel out. And so what you get is that tanh is actually e to the x minus e to the negative x over e to the x plus e to the negative x. But I don't remember it that way. I remember it as sinh over cosh. Okay, so I remember the definitions of sinh and cosh, and then I remember the definition of tanh is sinh over cosh. And then sech, hyperbolic secant, is 1 over cosh. Okay, so that's just the reciprocal of cosh there, kind of like secant is 1 over cosine. Cotangent is cosh over sinh. Okay, and if you work that out, this is what it is. And cosech Okay, hyperbolic cosecant is 1 over sinh, 1 over hyperbolic sine. Okay, I'm not going to worry about you can look up the graphs if you want, but I'm not going to worry about those. In fact, you might wonder, why are we using all this terminology that kind of sounds like sine, cosine, tangent, all these trig functions? Well, it turns out we have a lot of the formulas are similar. We already mentioned about the derivatives of sine and cosine. The one difference there is that the derivative of cosh is positive sinh, whereas the derivative of cosine would be negative sine. So notice there's no negative here. Okay, all the other derivatives are similar. Just like the derivative of tangent is secant squared, the derivative of tanh is sech squared. Okay, and you can figure these out for yourself. They're not hard to actually derive these. Take a derivative, simplify it down, and you'll see it's this. Okay, just like the derivative of cotangent is negative cosecant squared, the derivative of cotanh is negative cosech squared. In fact, all the derivatives are exactly the same, except this formula is off by a negative. Remember, the derivative of secant is secant times tangent, whereas the derivative of sech is negative sech times tanh. Okay, so there's a negative there. So this one, for the hyperbolic functions, has a negative, whereas the ordinary trig ones don't. And then the one other formula that's different is this one, where the hyperbolic ones don't have a negative, whereas the original trig functions do. Okay, so the derivatives are very similar. Okay, and of course, for every derivative formula, you get an integral formula, right? The fact that the derivative of cosh is sinh means that the integral of sinh is cosh. Okay, and the fact that the derivative of sinh is cosh means the integral of cosh is sinh. Okay, the fact that the derivative of tangent or tanh is sech squared means that the integral of sech squared is tanh. Okay, of x plus c. Okay, so every derivative formula gives you an integral formula, so we have these. Okay, so how could I ask this on the test? Okay, I'm sure that's what you're wondering. These didn't show up on any of the quizzes, so I thought it'd be good to go over this. So find f prime of x if f of x is x cubed plus 7x times cosh of 5x. Okay, so what we need to use here is the product rule. So we do the first function times the derivative of the second plus the second times the derivative of the first. Okay, well, the first function is x cubed plus 7x. The derivative of cosh of 5x would be sinh of 5x times 5, right? Just by the chain rule, right? The fact that the derivative of cosh of x is sinh of x means the derivative of cosh of 5x will be sinh of 5x times 5. Okay, and then plus the second function, cosh of 5x, times the derivative of the first, which would end up being 3x squared plus 7. Okay, now another one is, how do we do the derivative of tanh of ln of x? Now this is not tanh of x times ln of x, so that we're not going to use the product rule here. This is tanh of ln of x, so we're going to use the chain rule. Well, the derivative of tanh is sech squared, so the derivative of tanh of ln of x would be sech squared of ln of x times the derivative of ln of x, which is 1 over x. Okay. We could also do an integral or two here. How do we do the integral of x squared times sinh of x cubed? Okay, well, notice in this case we can do a u substitution. We let u be x cubed, and then du would be 3x squared dx. So notice we have the x squared that we need. Okay, I rigged this up so that we would have the x squared out there. If we had only an x, or if we had an x cubed, or x to the fourth, or if we had nothing out front, then this would be much harder to do this integral. Okay, but I rigged it up so this works out. So notice what we need is a 3x squared dx here to turn into our du. We have everything except the 3. So we put in the 3, and then we'll put in a 1/3 and bring the 1/3 out front. Okay, the 3x squared dx turns into the du. Okay, the 1/3 stays the same. And what we have inside here is sinh of u. Okay, well, the integral of sinh of x dx is cosh of x. The integral of sinh of u du will be cosh of u. Okay, that's just a dummy variable here. It doesn't matter whether you're using t or x or u. Okay, the integral of sinh of u du would be cosh of u plus c. So we have 1/3 cosh of u plus c, and then plug in what u is, right? U is x cubed. Okay, and you can check your answer by taking a derivative. What's the derivative of 1/3 cosh of x cubed? If you work out the details, use the chain rule here, you end up getting the original integrand right here. Okay, and finally, what's the integral of hyperbolic cotangent? So notice that's not anywhere in these formulas up here. Okay, what's the integral of cotang? Okay, it's not any of these things here, but we can figure it out without too much trouble. Just like if we're doing what's the integral of cotangent. Okay, if we want to do the integral of hyperbolic cotangent, it's very similar. We write cotang as cosh over sinh. Okay, that's the definition of cotang. Okay, but then we do a u substitution, letting u be the denominator. U is sinh, so du would be cosh of x dx. So notice what we get is the integral of 1 over u du. You might wonder what happened to the cosh. Well, the cosh of x dx, that whole thing turned into the du. Cosh of x dx became du. And then this down here is just u. So all we're left with in the top is 1. Now the integral of 1 over u du is natural log of u, or natural log of the absolute value of u, plus c. And then just plug in what u is. Okay, u is sinh of x. Okay, so that's the answer. Okay, so really for hyperbolic functions, you need to know these things. You need to know the definition of sinh and cosh, and then the definitions of these other ones just based on sinh and cosh. Okay, and then know that the derivative of sinh is cosh, the derivative of cosh is sinh, and it might be helpful also to know, say, the derivative of tanh is sech squared. Okay, so therefore the integral of sech squared is tanh, and so on. Okay, the fact that this is a take-home exam, you'll have these formulas with you, so I mean, it's good to remember them, but at least for this exam, you'll have them. Okay, now a couple other questions that were asked about, say, homework problems were, first of all, this one here. So notice this is, we're trying to find the limit as x approaches infinity of x times e to the negative x. So this is one where we're going to need to use L'Hopital's rule, because as x goes to infinity, we get an indeterminate form here. As x goes to infinity, e to the negative x is going to go to 0. Right? If you put bigger and bigger value in for x, e to the negative x is going to get closer and closer to 0. Whereas x itself will blow up to infinity. So we have like an infinity times a 0. So what's infinity times 0? Well, it depends. It's what's called an indeterminate form. Okay, it could end up being a number like 7. It could be infinity. It could be 0. It could be anything. Okay, it's indeterminate, so we have to figure out what it is for this specific problem. Well, this one's fairly simple. We can just write x times e to the negative x as x over e to the x. Okay, e to the positive x. Then notice we have an infinity over infinity type of indeterminate form. So we can use L'Hopital's rules. You can only use L'Hopital's rule if it's infinity over infinity or 0 over 0. And by the way, it could be plus infinity over plus infinity. It could be a plus infinity over minus infinity. It could be minus infinity over minus infinity, or minus infinity over plus infinity. Any one of those you can use L'Hopital's rule with. Okay, so L'Hopital's rule says just take the derivative of the top, derivative of x is 1, and the derivative of the bottom, derivative of e to the x is e to the x, and this limit should end up equaling this limit. Okay, well notice as x goes to infinity, now the denominator blows up, so we get 1 over infinity essentially, which is really 0. Okay, so in this case, the infinity times 0 sort of ended up giving us a 0 as our final answer, but it doesn't always do that. Okay, well, another one. This one's a little bit more involved here. So this is number 25 from section 6.5. Somebody had asked about this one. Find the limit. What's the limit as x approaches infinity of 1 minus 3 to the x, or 3 over x, to the x power? So notice as x goes to infinity, 3 over x goes to 0. So what you have inside here is 1 minus 0, which is really 1. And then as x goes to infinity, this exponent here will go to infinity. So what we have is a 1 to the infinity type of indeterminate form. And if you have an indeterminate form where it's an exponent like this, so like 1 to the infinity is one of them, 0 to the 0 is another one, infinity to the 0 is the other one. So I think there are 3 of them. 1 to the infinity, 0 to the 0, or infinity to the 0. Okay, all of those are indeterminate. Okay, so what do we get when in this particular case? Well, when you have one of those type of indeterminate forms where you have an exponent, the way I do this is to let L be the limit that we're looking for. Okay, and the question is, what's L? Okay, what is L? That's what we're trying to find, is what's L? L is this limit. Okay, well, if we take a natural log of both sides, natural log of L equals natural log of the right side. And the fact that natural log is a continuous function on its domain means that you can pass the limit through it. Okay, so that natural log of the limit is the same as limit of the natural log. And the whole point of doing the natural log is so that we can do this next step where we bring this x out front. We make the exponent out front. Okay, we get rid of the x as an exponent and bring it out front where we're multiplying. So we have x times natural log of 1 minus 3 over x. Okay, well notice as x goes to infinity, again, 3 over x is going to go to 0, so 1 minus 0 is 1, and natural log of 1 is 0. Okay, so as x goes to infinity, we have like an infinity times a 0. Okay, that's another indeterminate form. And when you have an infinity times 0 or 0 times infinity, the way you do this is to rewrite it as a fraction. So instead of doing ln of 1 minus 3 over x times x, we can do that thing divided by 1 over x. Okay, and now as x goes to infinity, we're going to get a 0 over 0. And when you have 0 over 0, you can use L'Hopital's rule. So with all these indeterminate forms, you try to write it in a way where you can use L'Hopital's rule. Okay, that's the usual process. Okay, so we take the derivative of natural log of 1 minus 3 over x. That would be 1 over 1 minus 3 over x times the derivative of 1 minus 3 over x, which turns out to be this. Okay, you can check it. Negative 3 over x is the same thing as negative 3x to the negative 1. If you take the derivative, you're going to get positive 3x to the negative 2, which is this. Okay, the derivative of 1 over x, if you work it out, and really 1 over x is like x to the negative 1 power, the derivative ends up being negative 1 over x squared. Okay, it's really negative 1 times x to the negative 2 power. Okay, well, if you work this out, notice dividing by this fraction is like multiplying by its reciprocal. Okay, and so notice when we take this and flip it and bring it out here, these x squareds will cancel. We still have that negative. So this whole thing will simplify to be negative 3 over 1 minus 3 over x. And now as x goes to infinity, now we take the limit. By the way, notice I'm writing the limit as x goes to infinity every time. If I didn't write that, and I just said, oh, these things are all equal to each other, it wouldn't be true. Okay, for example, this step here, we're going from here to here. It's not true that this is equal to this, but it's true that the limit as x goes to infinity of this is equal to this. Okay, we use L'Hopital's rule there. Okay, but notice as x goes to infinity, what we get here is negative 3 over 1 minus 3 over infinity, essentially, which really is 0. So this ends up simplifying down to negative 3. Now, our answer is not negative 3. It's ln of L that was equal to negative 3, right? So ln of L equals negative 3. What that means is that L is equal to e to the negative 3rd power. Okay, so remember, there's this logarithm has an invisible e down here. E to the negative 3rd equals L. Okay, and so e to the negative 3rd is like 1 over e cubed, so it's about 0.049787 and so forth. Okay, so that L'Hopital's rule is a little bit more involved, and it tends to be that way when you have indeterminate forms that are like exponents. Okay, again, like 1 to the infinity or 0 to the 0 power. Okay, almost done here. So a couple other questions. So 6.7, number 25. So this is about the inverse trig function. So find dy dx if y is tangent inverse of x cubed. Now remember, the derivative of tangent inverse of x is 1 over 1 plus x squared. Okay, we derived that in class. And the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. This one has a square root, notice, the tangent inverse doesn't. Okay, so we derived those in class, and those are the two that I want you to remember. If this were an in-class quiz or exam, I would have you memorize these formulas. Okay, well, what's the derivative of tangent inverse of something? Well, the derivative of tangent inverse of x is 1 over 1 plus x squared. The derivative of tangent inverse of something is going to be 1 over 1 plus that something squared. Okay, the something here is the x cubed. But then times the derivative of the something. Right, so that's according to the chain rule. Okay, so what we get, if you simplify this, would be 3x squared over 1 plus x to the 6th power. Okay, but you can leave your answer like this. That's totally fine. Okay, and also, here's an integral problem where, in fact, two more problems here. Here's an integral problem, 6.7, number 41. What's the integral of secant squared over the square root of 1 minus tangent squared of x? Okay, well, just looking at this, it looks confusing. It looks like, oh, there's going to be some crazy trig identity we're going to have to use or whatever. Well, it turns out if we just do a u substitution where we let u be tangent of x, du is going to be secant squared of x dx, which is exactly what we have up here. So the secant squared x dx becomes the du. What we have left is the integral of 1 over the square root of 1 minus u squared, okay, where u is tangent. Well, this is just sine inverse of u. Okay, the integral of 1 over the square root of 1 minus x squared dx is sine inverse of x plus c. But that variable is just a dummy variable, so we could do it with a u, and we get sine inverse of u. Okay, and then plug in what u is. Okay, it was tangent of x, so our answer is sine inverse of tangent of x. Okay, and by the way, that can't simplify nicely using the triangle method. If this were sine of tangent inverse of x, we could use that little triangle method to simplify it. But sine inverse of tangent of x, we have to just leave it like this. By the way, you could check your answer by taking the derivative of this. Okay, and then you should get this. It shouldn't even involve much simplification at all. You should get this as your answer. Okay, one last thing. So this was not an actual problem from the book, but somebody asked about what about derivatives of, like, instead of just e to the x, right? The derivative of e to the x is e to the x, and you definitely need to know that for the exam. What about something like the derivative of 3 to the x? Well, the derivative of 3 to the x is 3 to the x times ln of 3. Okay, so how would we do something like this? Right, what's the derivative of sine of x times 3 to the x? Okay, well, we use the product rule. So we do the first function times the derivative of the second, plus the second function times the derivative of the first. And remember, the derivative of 3 to the x is 3 to the x times ln of 3. Okay, and so this is what we get as our answer. Okay, well, that's a little bit of review, so I haven't gone over absolutely everything for the exam, but it's a take-home exam or an at-home exam, and so so you can use your book and your notes. But let me know if you have any questions, and good luck on the exam.